Alright, greetings fellow earthlings. Another video. Just pleading with you to be reasonable. Recognize that, in our progress, in our effort to understand the universe, the earth, the world we exist in, how it functions, we've made some mistakes. And frankly, science, the science of physics in particular, has gone on, kind of wild goose chases. Kind of call them Sasquatch chases, actually. Just kind of wooey fun, make the truth fit our expectations kind of crap. And so they have some really stupid notions. And one of them is that there's this Leibnizian view of the universe where there's solitons and monads and all kinds of weird spiritual stuff floating around in all of matter because God says so. And God must be right, and God created a perfect world and all that nonsense. And physics is basically part of that. It's just a subdivision of that religion. And sadly, pitifully, really. And I'm just pleading with you to grow a brain, be reasonable, recognize that that just doesn't work. It's unnecessary, it's bad science, it's pseudoscience, it's religion, it's crap. And it's time to fix it and move on, to a better real model of the universe instead of some wacky ESP-driven superposition, singularity, all these little fun words, kind of wackaverse. So anyway, I have gone over this and over this, trying to explain that kinetic energy doesn't work, doesn't fit, it creates all kinds of paradoxical nonsense, and you remain unpersuaded. So we haven't talked much about hydraulics, but it sort of demonstrates the point. So I'll play this little clip from how a hydraulic jack works, just to explain the fact that, what goes in has to come out, frankly, and you can't make energy. And kinetic energy makes an absolute mess of such a simple device, and momentum works perfectly reasonable. And the guy basically says that, without saying it. I mean, he uses the word energy, conservation of energy, and what he's talking about is conservation of momentum, because the jack doesn't conserve kinetic energy. It just doesn't do it. Alright, so we'll play a little bit of it.
Exerting a small force on the pump piston, which have a small cross-section area.
So again, he's saying force as if all you can really say is there's a smaller rate of force on one side, and the rate of force will be different on the other side. So it's 9.8 meters on one side and 3.2 meters on the other side. Kind of an argument that you're basically, because of the difference in the surface area you're creating, let's just say it's a 3-to-1 relationship between the surface areas, and that's basically a law of the lever, and that's basically the differential, and all you're really saying is you're cutting the rate by that 1/3, or if you use the net force, you're going to end up with the same exact net force. You're just going to have it in a different configuration, but it's going to be the same amount of total energy.
Will generate a pressure in the fluid. According to Pascal's law, a change in...
So you don't need Pascal. I mean, this is something we've confirmed over and over and over again, so we don't need a law anymore.
Pressure applied to a fluid in an enclosed system will be evenly distributed throughout the fluid and transmitted everywhere in the system.
Well, it's almost anything will transmit eventually, and it just means how quickly. So fluids obviously transmit pressure very quickly because they're non-compressible, but air will compress in one thing, and eventually the air compression gets to the other side. So it's anything can be used as a conduit. So you can just basically say you can have a very good wire for transmitting electricity, or a poor wire for transmitting electricity, or something like that, but the electricity is always somewhere. It doesn't non-exist. So any energy you create has to be dissipated as some form, whether it's heat or some sort of dissipation. It has to go somewhere. And fluids just make sure it goes where you want it to go.
Therefore, the pressure generated by the pump piston also acts on the second main piston. However, the main piston has a larger surface area. Increasing the surface area leads to a larger force.
So there's no larger force. So this is just nonsense. There's no larger force. This doesn't happen. It doesn't happen. There's no extra energy produced. You're just changing, you're moving a small mass in one case, you're moving a big mass in the other case, and momentum is perfectly conserved by the device. So let's say you had a weight of surface area in this case, and weight of 1 for the small one and 3 for the big one. You can understand that all that's going to happen is the momentum is going to be converted. So you're going to go from something that has a 1 mass and a 3 velocity to something with a 3 mass and a 1 velocity. And if kinetic energy was conserved, that wouldn't work, because you'd end up with 9 elements of force in one side and only getting 3 out of the other side. So obviously it doesn't fit. And if I go the opposite way, I would also have a big problem, in a sense. I start with 3 and somehow I get 9 out. And we know that can't happen, because that would be free energy. So momentum works perfect. Kinetic energy doesn't work either way.
For example, if the surface area of the main piston is 3 times larger than the area of the pump piston, the force applied on the main piston will be 3 times as much as the force applied on the pump piston.
So he says that, right? It's more force being applied, yet it doesn't move as fast or as high. So it only moves 1/3 the height, and it's only moving 1/3 the speed, and yet he's saying it's somehow 3 times the force. So what sense does it make? That's right, it doesn't make any sense.
But to respect the law of conservation of energy...
So he says respect the law of conservation of energy. So he's saying that somehow you have to respect it. Well, what law are you respecting? Clearly, kinetic energy fails. So if you're conserving the kinetic energy, the pump doesn't work the way it actually works. So the way it actually works, it can't respect conservation of kinetic energy. You either lose too much energy when the small piston, with its higher joule number, you get a lower joule number coming out of the other piston. And if you use the big piston to push the small piston, in the reality you're going to get far less than your expectation. You're going to push with less momentum on one side and get, you're going to get less out of the product in terms of your kinetic energy.
The displacement of the main cylinder will be 3 times less than the pump cylinder.
Right, so the displacement meaning the movement, frankly. So it's pretty much that simple. So, yeah, I mean, you could change this in all kinds of scenarios. Like I could make a big diaphragm like this and say I jumped on it. And then I could have a little tiny thing in the other piston, a very narrow, with a 100-to-1 ratio or a 1,000-to-1 ratio even of surface area. And like a lever, I could put a heavy weight on one side, and I could shoot a light weight very fast out of the other side. So, just not a big surprise. And again, he said the words conservation of energy, but you can't conserve kinetic energy in this circumstance. It isn't conserved. So the actual pump will not conserve kinetic energy. Just a fact. Doesn't do it.
Now let's see how the bottle jack...
Okay, so no point in going through the fact that it has little ball valves in it, and you're just pumping pressure from a big cylinder into a small cylinder or vice versa. And not very fancy in any way whatsoever. In terms of understanding that what goes in one side has to come out the other side, and the only thing that really comes out is momentum. Nothing else. Weight, pressure. That's all you're conserving, and there's no kinetic energy correlation to that. So like the gun and the bullet, the fact is momentum says the bullet has the same energy as the recoiling gun, and it's only the kinetic energy theory that says somehow I only put 2 joules of energy into the gun, and somehow I put 2,000 joules into the bullet, breaking Newton's third law. So I mean, it's it doesn't work. It's not good physics, and not being good physics means it's not good science. and people should move along and go find the real truth, which was the truth Newton knew, 300 years ago. Alright, so simple summation. The kinetic energy theory, if applied to this pump, does not accurately make predictions about what will happen. Okay, it'll predict that this will go much faster than it will, the heavy cylinder, because it has to equalize the kinetic energy that went in. Okay, so the light fast thing goes fast, it's light. It has a high joule number. They have to somehow make the same joules pop out this other side. It won't happen. Okay, so it won't predict correctly. And then the vice versa is when they push this big cylinder, the fact is that the momentum is going to be conserved, and there's not going to be any sign that they can produce this very little amount of kinetic energy out. They put 2 joules in. They're going to get a lot more than 2 joules, okay, by the kinetic energy theory out. So this is going to perform, beyond those expectations. The lighter object is somehow going to be producing more energy than went in, okay, by joule numbers. So the predictions are going to be completely wrong, and momentum is going to completely and perfectly predict the actual function of the device. So kinetic energy will make completely wrong predictions, and if you conserve it, and momentum will make perfectly correct predictions. Just a fact. So why are they clinging to a theory that can't survive a mechanism this simple? And it's a good question. Why are they clinging to it? There's no evidence it takes 4 times the energy to go twice as fast. There's no evidence that it takes 9 times the energy to go 3 times as fast. There's no evidence it takes 16 times the energy to go 4 times as fast. And you can just keep going until you get to preposterous numbers where you can actually say 1,000,000 times the energy. You can say that, and it just won't be true. Alright, it will remain untrue. And so, you're telling me you're reasonable people, and you won't concede that, well, your theory of energy should be able to explain a device this simple. It should be able to accurately predict what will happen. And it doesn't. I shouldn't have to say more. So I won't. Yeah, since I shouldn't have to. Please, 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 stop being silly. Just accept the truth. Yes, it's mundane. Yes. But it's the truth.